Hello everyone, welcome to week 3 of Fundamentals of Micro and Nanofabrication course. So this course is run on NPTEL and is taken by Professor Shankar and Professor Shishobhan from Center for Nanoscience at ISC. I am the teaching assistant Mukta and I would be conducting today's tutorial session. So in week 3 we covered advanced topics in ion implantation and native films. So the first problem, we'll be talking about the CMOS process. So that is silicon on insulator. How do we, the recipe for fabricating a silicon on insulator wafers. So silicon on insulator wafers are commonly used in CMOS devices, and the general cross sections of are basically 100 nanometers of active layer of silicon. Then there will be 200 nanometer buried oxide. This can vary from application to application. And then there is a thicker substrate, silicon substrate again. So basically we have silicon, silicon dioxide and another silicon. So this is the substrate. Then an oxide layer separating the substrate from the active silicon layer. For the purpose of this problem, we take this active layer to be 100 nanometer and SiO2 to be 200 nanometer. And then the silicon is 500 nanometer, substrate silicon. Okay, so all the devices will be made in this active layer of silicon. And the method of making such a stack, that is such a wafer, is called CMOS. So this is not very predominantly used these days. We have bonding methods or other kinds of mass manufacturing methods, but this was used before, and we'll see what are the challenges that are faced when we use this recipe. So the general recipe is that we do an oxygen ion implantation in the silicon wafer. So if this is my silicon wafer, I'll bombard it with O plus ions, oxygen ions, and then we do a cleaning step. In the cleaning step, basically there will be some oxygen ions that have been implanted in silicon, and however these oxygen ions, because we are doing ion implantation, they will introduce a lot of defects in the silicon. So this is not the kind of film that we want. On top of that, this top layer, which had directly seen the oxygen atoms, oxygen ions, it will have a lot of defects, and then we want to make the devices in this layer. So it's not feasible to make devices in a defect prone layer, right? So we need to reduce the defects. Now to reduce the defects, we do annealing, and so basically we bake the wafer at a higher temperature that results in annealing and internal thermal oxidation. Because of this, we get well-defined layers in the stack, and there is also additional oxide layer on top. So this is again SiO2. So this is the oxide that we don't require. So then we again clean it to remove the surface oxide film. So that is the general idea. So finally we have gotten the stack that we wanted to start with. Okay. So this is the general process. So what all things can go wrong here? So the first problem is asking the following. So the figure shows wafer failure as a function of anneal temperature and oxygen implant dosages. So first of all, what do we mean by wafer failure? When do we say that that we have not got the required wafer? So as you can imagine, if we have a lot of defects in the active region, or if the SiO2 like the interface is not very smooth, SiO2 silicon interface, and it is we should also avoid the interface defects, right? So it should be a smooth interface, and the active layer should be defect free. So all those things should be there. Only then we say that the wafer has not failed. And yeah, so this failure rate can be plotted as a function of anneal temperature and oxygen implant dosages. So it depends on these two things primarily. So how much oxygen we are bombarding and what is the temperature at which we are annealing. So if you remember, I said that annealing is used to reduce the defects. So high temperature anneal actually reduces the defects, but it's not that simple. So we have to check for what oxygen implant dosages and what anneal temperatures we are getting the best um, the best like yield in terms of failure rate. So we require zero failure rate or near zero failure rate. So if you look here, so this is oxygen dose. As I'm going on increasing oxygen dose, the failure rate falls and then increases again. So there is some optimum oxygen dose for which the failure rate is minimum. Also, the failure rate is also a function of temperature. So if you look here, um, for 1300 degrees Celsius, the failure rate is quite high. But however, as we go on increasing the temperature, the failure rate is reducing. Right. So, um, so from this graph, one thing we can notice, we need oxygen dose of the order of 10 power 17 per centimeter cube to create buried layers. So this is very high compared to all the previous doses that we have seen for ion implantations for doping and everything. Yeah, whenever we saw boron doping or n-type doping. So in those cases, the dose was not this high. So why isn't that in this case we have to put so much high dose? Because as we know, higher dose will eventually lead to higher number of defects. So why are we going for these high doses? Assuming the buried SiO2 layer is 200 nanometer thick, can you justify the need for such high dose implants? So yeah, so basically they're asking us to calculate how much dose is actually required for 200 nanometer thick SiO2 layer. So if you remember, we had a silicon active layer, and below this silicon active layer we have 200 nanometer thick SiO2 layer. So how much dose of oxygen is required to get this 200 nanometer thick layer? To calculate this, first thing that we need to look at is the silicon density. Okay. So idea is, if we know the silicon density, then we can know how many then we can know how much oxygen is required per unit area to uh, to get a 200 nanometer thick layer. So the way to go about this will be to first take silicon density. So we can get this from the internet. For now, let us assume it to be, it's of the order of 10 per 22 atoms per centimeter cube. So if you just Google on the internet, you will get something like 2 point something grams per centimeter cube. Now, if you so this number is in grams per centimeter cube. So you know this, and then you know the molecular weight of silicon. From that, you can get the number of atoms per centimeter cube. So this is like 1 mole per centimeter cube. 1 mole has 2 point so many grams, right? So using that relation, so you can get the silicon density in terms of atoms per centimeter cube. Once we have that, now the next thing for us to do is to calculate how many oxygen atoms will be required. So we need 200 nanometer thick layer of oxygen, right? So 200 times, so 200 nanometer means 200 into 10 power minus 7 centimeters, right? Because this is in centimeter cube, I'll keep it in centimeters. So this is the thickness. So this times the silicon density will give me what? Will give me the number of silicon atoms that will be required to form the silicon SiO2 layer. So this is not number of silicon atoms, since we are multiplying only with the thickness. So this will be number of silicon atoms per unit area. Give some time to it, you will understand that why I am putting this per unit area and why this relationship is valid. So what I'm basically doing is I'm just multiplying the thickness to the silicon density. So from this I get the number of silicon atoms per unit area. So that will be nothing but 2 into 10 to the power 22, 24 minus 7. How much is that? 17, I guess. Right. So that will be 2 into 10 power 17. So if this are the number of silicon atoms, how many will be oxygen atoms? Therefore, number of oxygen atoms will be equal to 4 into 10 power 17. Right. So now we know why we need that high doses. So this is atoms per centimeter square. So if you look here, this is also close to 4 to 10 power 17, where we get the minimum failure rate. So that is the thing. So we need that many atoms to get a 200 nanometer thick. So here, if you remember, in the previous cases when we were doping, we just need to create a few defects, or the dopants need to go and occupy some substitutional sites. But here we are forming a completely different layer. So SiO2 layer is like an alloy between silicon and oxygen, and so that's why it will require that many number of oxygen atoms. We're not just occupying the substitutional sites or forming some sort of defects. We are making a completely different new layer. So that's why we need such high dose implants. Okay, so it's a continuation of the previous problem. The anneal temperatures in the CMOX process are 1300 to 1350 Celsius, degree Celsius. So why do they need to be so high? Again, if you look here, we are going to higher and higher temperatures, and when we go to higher temperatures, we are seeing that the the failure rate is reducing. Like compared to the circle, the diamond is doing better and the square is doing the best. So clearly we can see that higher temperature anneal is giving us better results in terms of defect densities and failure rates. So why is that the case? Simply because um, oxygen ion implantation will produce lot of defects. So because it's producing a lot of defects in both the SiO2 layer and the active silicon, so this will result in so we need to anneal. Okay, so next what they are asking. Ultimately, the CMOX technology failed. The very heavy implant caused way too much damage in the active silicon layer, leading to poor quality devices. During the lecture, we discussed how high dosages were easy to anneal due to solid phase epitaxy. Why does that argument fail here? Okay, so solid phase epitaxy is when we convert an amorphous material that is deposited on, say, some silicon substrate or some other crystalline substrate, and then because of the crystalline orientation of the substrate, the amorphous material that is deposited on top of it also tries to align itself to the stoichiometry of the substrate. So that is why we get a transition from the amorphous behavior to the crystalline behavior of the deposited film. But when we are depositing this silicon, in this case we are not depositing, sorry. In this case we have a silicon film on top of silicon dioxide, and then there is a substrate of silicon. So we know that the silicon dioxide that is thermally grown, or in this case we get it through the ion implantation, this silicon dioxide is amorphous in nature. Since the silicon dioxide is amorphous in nature, the top layer silicon is seeing amorphous silicon dioxide as the substrate. So it doesn't have any crystalline substrate to align its its atoms do. So because of that, the argument will fail here because um, to the main requirement for solid phase epitaxy is that the substrate is crystalline. So here this silicon is crystalline. However, there is an amorphous barrier, oxide layer, because of which the top layer, active layer silicon, uh, cannot anneal and cannot undergo solid phase epitaxy during annealing step. So that is why we can't do much better here. We can't completely remove the defects in the active layer of silicon. Okay, that was about the CMOX process. So, so now let's go to the next problem. The problem is a multiple choice question. Which of the following cannot help reduce channeling in ion implantation? So, yeah, we remember ion implantation. In ion implantation, the ions sometimes, uh, or a lot of times, they enter a channel, and because of that, we see the deposition profiles have tails like that, right? So, if this is a thickness, then the concentration of the ions will not be a perfect Gaussian, or right, it will have a tail. So so which of the following cannot help reduce channeling? So to reduce this channeling effect, so why is this channeling happening? Channeling is happening because we have a crystalline silicon substrate, and in the crystalline substrate there will be um, the ions will encounter collisions, and since the orientation is very stoichiometric, they might encounter collisions and enter a channel. So in this channel, the number of collisions that they face is relatively lower than if they were going in some other direction. Okay, so because of that, we see these tails. So the thickness is not as we expect. Then what can help reduce this? So think about sample rotation. So what will happen? See, say I am sending some ions, and these ions are seeing some stoichiometry like this. If I rotate the sample, say this is my xy plane, if I just rotate it, then what will they see? They will see something like this. Say, sorry. Again they can encounter channeling, right? So sample rotation cannot help reduce channeling. What about pre-implant of silicon in silicon at high doses? Okay, so what this means is that we first implant silicon inside the silicon substrate. So that will create defects in the silicon. So whenever there are defects, it will so the silicon crystal, it won't be perfectly crystalline. So it will start becoming a little bit amorphous in nature, because of which uh, the ions won't see perfect channels of silicon atoms. However, the channels will get distorted, and finally the channeling effect will reduce. So this will help. Sample tilt. So this was also discussed in class. Sample tilt helps because now they won't be able to see the perfect channel like these 5 dots. They will be seeing some random arrangement of dots based on of silicon atoms based on the tilt. So higher the tilt, the lower will be the channeling. So this helps. Screening layer of SiO2. So SiO2, if you remember, is amorphous. So amorphous SiO2. So since most cases we are not able to grow quartz on silicon, so this silicon dioxide that is grown on top of silicon or deposited on top of silicon will be amorphous. So since this silicon dioxide is amorphous, whenever some ion hits it, say in 90-degree angle, it will scatter it in different angles. So it acts like basically giving a sample tilt, but in all possible directions. So that will again reduce the ion implant. The channeling. So screening layer of SiO2 also helps. So which of the following cannot help reduce channeling? It's sample rotation. Which of the following is correct as per the Deal groove model of native oxide growth in silicon dioxide? Silicon dioxide and silicon. Uh, okay, okay. So diffusion of H2O is faster than O2. So diffusion basically depends on the diffusivity or diffusion coefficient D, and it's known that the diffusion coefficient of oxygen is higher than H2O. So diffusion of H2O is faster than O2 is a false statement. Parabolic rate constant depends on crystal orientation of wafer. Okay, so if you remember, there were two rate constants when it came to Deal Groove model. One was the parabolic rate constant, and the other one was the linear rate constant. So, so when we start to grow thermal oxide on top of silicon, in the initial stages, only a thin layer of oxide is formed on top of the silicon. In this phase, what happens is um, the diffusion of diffusion. So we are putting oxygen from top, right? So diffusion of oxygen is not the problem. However, the reaction is limited by the rate of reaction at the surface. So so and this regime is basically the linear rate constant regime. So it will just be some k, that is the linear rate constant, times the number of oxygen species at the interface. So that, say, concentration of O. Okay, so this is the linear regime. But as we go on building the thickness of oxygen, so as the SiO2 thickness starts to increase on top of silicon, then the reaction is limited by diffusion of oxygen species through the SiO2. Okay, so now in this case, uh, it's not limited by the so it's not a linear regime anymore. It goes to the parabolic regime. And as you can expect, so in this case, it's not the oxygen that is reacting with the silicon that is what that is limiting the reaction or limiting the oxide growth or silicon dioxide growth. What is limiting the growth is the diffusion of oxygen into the silicon, into the SiO2. So in this case, this is the actually where the parabolic rate constant. This is the regime of parabolic rate constant. So now intuitively, if you think, parabolic rate constant depends on crystal orientation of wafer. So why will it depend on crystal orientation of wafer when it is not limited by the mm, silicon substrate itself? It's limited by the diffusion. Diffusion is not critical to the crystal orientation of wafer. So this is also false. So linear rate constant is same for wet and dry oxidation. Okay, if this was true, that would mean that the linear rate constant will be same when we are doing dry oxidation with O2 gas or with H2O liquid. But that is definitely not the case because of the fourth point, that is solid solubility of H2O in SiO2 is higher than oxygen in SiO2. So if the solid solubility of H2O is higher in SiO2, naturally more oxygen will reach the silicon surface, and the rate limitation will so when linear rate constant is when we are having thin films, right? So uh, so it is basically reaction rate limited, and this limitation will be reduced in case of H2O, because H2O will reach the silicon surface faster because it has highest solid solubility in SiO2 compared to oxygen. So this is in fact true. Okay, so what I mean to say is, so now this is SiO2, right? And this is, we are putting either H2O or oxygen gas. So oxygen gas has a lower solid solubility in SiO2. So less amount of oxygen gas will be able to reach the silicon surface. Compare that to H2O. H2O, more oxygen species will be able to reach the silicon surface because solid solubility of H2O is higher in SiO2. So because of this, the linear rate constant will be higher because the reaction will speed up at the interface. So this is true. And sorry, this is false. It's not the same. It is higher for H2O. And this is true. Solid solubility of H2O and SiO2 is higher than oxygen and SiO2. Okay. Okay. So this is about finding the pilling Bedworth ratio. Trivalent metal has the following properties. They have given the properties. A is the metal and A2O3 is its oxide. So we have to find the pilling Bedworth ratio. So if you remember, the pilling Bedworth ratio was the molar volume of oxygen, sorry, the molar volume of the oxide upon the molar volume of the metal. Or in the case of SiO2 and silicon, we had found out the pilling Bedworth ratio in the class, and it was molar volume of SiO2 upon molar volume of silicon. So in this case, we just replace the SiO2 by A2O3 and silicon by A. So yeah, so to start with, we have to find first this PB ratio. We have to first find the molar volumes of both these species. To find the molar volumes, it's pretty straightforward. They have given us the density, they have given us the molecular weight. So 1 mole of 1 mole of A will weigh 26.98 grams. So how many moles are there in 1 centimeter cube? How do you find it? Or rather, if I say how much volume will be required for 1 mole? So 1 mole weighs so much, and they have given the density. Then how much volume will be required for 1 mole of A? So what will be the volume per mole for both these species? So volume per mole will be in centimeter cube, and it will simply be nothing but 26.98 divided by 2.7, and that will come out to be something around 9.99 like that. And in this case for A2O3, it will be 97.11 divided by 3.965, and that will come out to be something around 24.49. So this will give us the pilling Bedworth ratio. Somewhere around 2.5. Okay. Next question is native oxide growth in thicker SiO2 films is limited by. So as we have already discussed this, in thicker oxides, SiO2 film, the native oxide growth of SiO2 films is limited by the diffusion. Basically, it has to cross a lot of SiO2 before it reaches the silicon. So the diffusion process limits the. So there are two things, right? One is the diffusion, another is the rate at the surface. So in case of thicker oxides, the diffusion is the limiting case, and in case of thin oxides, the surface reaction is the limiting case. Okay. Okay, so now we have to tell if the statements are true or false. Pilling Bedworth ratio. So if you just now we discussed pilling Bedworth ratio of silicon dioxide is such that silicon dioxide takes more volume than the same amount of silicon. Is this true or false? Turns out that it is true. It is in fact true that SiO2 has a lower density compared to silicon, because of which it, it occupies more volume, almost twice the volume when compared to silicon. Uniform profile of dopants can be created using ion implantation, though multiple implants through multiple implants with multiple dose and energy. Okay, so if I want the dopant profile to be something like this as a function of thickness, so it's a quite uniform profile. This we can achieve using ion implantation through multiple implants with multiple dose and energy. So to we can imagine that we can do multiple implants at different uh, with different energies. So energy will determine how much our ions will penetrate, and dose also will determine what is the peak dose. And using the right combination of dose and energy and the number of implants, we can get a nice uniform profile. So that is true. Annealing causes more damage to the silicon lattice than implantation. This is definitely false. We are actually doing annealing to reduce the damage. So implantation is what that causes damage, and annealing is used. Annealing is basically heating at a higher temperature, and that is used to reduce the damage. Basically, it helps in bringing the silicon atoms back to the lattice positions and reduce the defects caused due to ion implantation. Oh, more true and false problems. Wet oxidation has higher growth rate than dry oxidation, because diffusion of O2 is faster than H2O in SiO2. So this statement sounds quite counterintuitive. Wet oxidation has higher growth rate than dry oxide. That part is true, because diffusion of O2 is faster, but that doesn't make sense, right? If O2 would diffused faster, then dry oxidation should have been uh, have had higher growth rate, but that's not the case. So this is a false statement. Wet oxidation has higher growth rate than dry oxide, again correct, because solid solubility in SiO2 is higher for H2O than O2. So this is true, as we have already discussed. Native oxide SiO2 grown on silicon at 1000 degrees Celsius is less dense than quartz, but electrically forms an excellent interface with silicon. Okay, so this part is true that it is less dense than quartz. Quartz is a crystalline form, and the native oxide that we grow is amorphous, and that's why it takes more space, because it's not perfectly aligned like all domains. Like it's not perfectly crystalline, basically. But it electrically forms an excellent interface with silicon, and that is also true, and that's the reason why silicon is so popular, uh, because of the native oxide properties, and because even though it is amorphous, it is still forms a very good interface in terms of defect densities and even electrically. So that is why um, this statement is in fact true, and that's the main reason why, like one of the main reasons why silicon is so popular in for the fabrication processes. Right. Interface defects, that is trapped charge at silicon dioxide interface, can be reduced by reducing sodium potassium contamination. So these are basically Na plus K plus ions, right? These contaminations can come from improper wafer handling, or even not cleaning properly, or even when you have cleaned properly, some amount of trace impurities, ionic impurities might come. So, but are these really specific to the interface? No, right? So these are most likely found in the bulk. The interface defects, that is the trap charge, are formed at the silicon dioxide interface because of the dangling silicon bonds. So yeah, so this transition from silicon to silicon dioxide, it will have certain defects, and those are called interface defects. And uh, they have nothing to do with the sodium and potassium contamination. So to handle these defects, there are different things. So this is false. Fixed oxide charge in SiO2 can be reduced by. Okay, so again, now we have an SiO2 grown on top of silicon, but the transition is defect prone, and we can have some SiOx in the middle that is formed. So like it will have more silicon, like this O2 might be O 1.8, 1.7, like that. So because we are diffusing oxygen from top and there will be silicon at the bottom, so there will naturally be a transition region, right? So this is the transition region. So in this transition region, because of this OX, so that means some of the uh, like not all the valencies are satisfied here. So fixed oxide charge in SiO2 can be reduced by, okay. So this this abnormality, so this SiOx will form some kind of defects in this region, right? Because it's not exactly SiO2 nor exactly silicon. So these defects can be reduced by like how can we reduce these defects? How can we make this perfectly SiO2? So for that, uh, by reducing sodium potassium contamination, this will definitely not work, because it's not because of that. Forming gas anneal, forming gas is basically H2 in N2. So some 10% H2 in N2. Uh, so this won't help here because it's not hydrogen that we require. Uh, we just require that. mm, Basically, the silicon to completely oxidize or completely be silicon. So we just require a proper separation between the two layers. Okay. The correct answer is actually high temperature annealing nitrogen ambient. So if you remember, this was taught in class uh, as a part of discussion on Deel's triangle. So professor had discussed that as we go to higher temperatures, the number of defects, or yeah, defects, let us keep it defects, as a function of temperature would fall down. So basically high temperature anneal would is a beneficial step for reducing the fixed oxide charge. So fixed oxide charge defects. Okay. Another thing that that was discussed was that this anneal uh, works better when we are doing it in nitrogen ambient. So if we do it in oxygen ambient, it creates more defects. But if we just do it in nitrogen ambient, say, then the number of defects will reduce. So even like once I've reached this stage, even if I do reduce the temperature in nitrogen ambient, then the number of defects will still remain the same. Okay, so basically if I had just done a nitrogen ambient, so this is when there is oxygen ambient, when I had done nitrogen ambient at this temperature, it would have dropped down. So basically it just means that we can do like how much ever oxidation that we want, and after this oxidation is done, if I just do a high temperature anneal in nitrogen ambient, then I get a perfect SiO2 layer on top of silicon, with minimum defects. So this part of SiOX will reduce and become very thin. So another form of defects is interface defects, that is trapped charge at silicon dioxide interface. Right, so this was fixed oxide charge. So this is in the oxide layer, SiO2 layer. So at the interface, SiO2 Si interface, there are defects due to the hanging silicon bonds. So there are some silicon with unsatisfied valencies. So how do we reduce these defects? So again, this is not the correct option. The correct option in this case is the forming gas anneal. So what happens in forming gas anneal is the hydrogen is the forming gas was what, H2, 10% H2 in nitrogen. So the hydrogen is the key element here. The hydrogen will diffuse through this oxide layer and reach at this interface and form bonds with this uh, like complete the valencies of the dangling silicon bond. So uh, because of that, there is a passivation that is happening, and that will reduce the interface defects. The next part is mobile charges in SiO2. So there is bulk SiO2 now that we have formed on top of, and this silicon substrate on top of silicon substrate. Now in this SiO2 we can get some ions like Na plus, K plus, like we were talking before. So these bulk impurities, so impurities in the bulk, how can we deal with them? How can we reduce them? So using different kind of oxidation, um, depends. If the setup is cleaner for dry oxidation, that might help, but in general that is not very helpful. Forming gas anneal, again, um, it's not much use because it won't be able to remove the sodium or potassium or any other kind of metal or ionic impurities. So that's not going to work. Annealing will not work because it will actually help in the diffusion of these impurities even further into the substrate. So no. Chlorinated oxidation at low temperature. So what does that mean? Sorry. Chlorinated oxidation at low temperature. So chlorinated oxidation means basically we are just making this Na plus ion react with Cl minus, so that we form some salts. Now these salts can't alter the electronic properties as they won't be mobile charge carriers. So basically, even metals, they will form some stable salts with chlorine. It's a very good oxidizing agent, and that is why this works for handling the mobile charges in SiO2. So that's it for today.